This is a 2 cents audio power amplifier chip, probably the world's cheapest audio amplifier. In this video, we will put it onto a PCB and see how good or bad it can be for only 2 cents, so stick around. This video is sponsored by JLCPCB, more on them later in the video. While searching for an audio power amplifier chip at JLCPCB for an old project rework, I don't know why, but I guess it was out of curiosity, I sorted the chips by price, and I was shocked to see this 2 watts 5 volts audio amplifier chip for only 2 cents. The price has increased a little bit, but for large quantities it's still under 2 cents. So I decided to give it a test. Speaking of the datasheet, and of course it's Chinese, however, all the relevant data can easily be extracted from this document, especially the typical application schematic diagram, which is listed here. However, there is also another English version for this datasheet from another vendor, which has almost the same information. Here is the project article. I will leave a link to it in the description. And here are the technical specs for this audio amplifier chip. It can be powered up using 2.2 volt supply up to 5.5, which is very convenient for single cell battery operated devices or USB powered devices. At 5 volts supply, it promises less than 10% total harmonic distortion or THD while delivering 1.5 watts of power into an 8 ohm load or 2 watts of power into a 4 ohm load. It has a shutdown mode for low power applications, click and pop filtering and protection. It has low BOM cost because it requires very few components other than the chip itself, and it's unity gain stable with external controllable gain. And now the question is, why 2 watts of power into a 4 ohm load at 5 volts should be impressive? And here is why. Let's say you have got a single cell battery operated device or a USB powered device, and you have maybe like 5 volts supply. This is our 5 volts DC. And here is our ground, and this is a typical audio amplifier output stage. We may have some sort of bias here, a voltage amplification stage here or VAS, and also an input stage or IPS, and then it goes our line in signal, and here is our audio amplifier. Given that we have only 5 volts, we will power up our amp by 5 volts and connect this to ground. And let's say this audio amp is ideal. We would expect a maximum voltage swing going out to our speaker of 5 volts peak to peak. But of course it's not ideal amplifier, so there will be some voltage drops here on this switch and here. So you would practically expect a maximum voltage swing that looks like this, which could be like 4.5 volts peak to peak, and this is what we can practically expect from an audio amplifier, given that we have only 5 volts supply. And let's see what does it mean in terms of power. So let's go to our calculator here. We have got like 4.5 volts peak to peak into a 4 ohm load. So we are speaking about like 0.6 watts of power. Going back to our chip, it promises like 2 watts of power into a 4 ohm load using only 5 volts. 2 watts of power into a 4 ohm load is equivalent to a maximum voltage swing on the output that maybe, I guess, yes, it's 8 volts peak to peak. And now the question is, how did they do it? How can this chip using only 5 volts supply to be able to output like 8 volts peak to peak to the speaker? And the answer is bridge tied load configuration, which this chip uses. Let's take a look at the schematic diagram, which indicates the internal structure of this audio amplifier chip. In a bridge tied load configuration like this, the audio amplifier is differentially driving the speaker. So the negative terminal of the speaker is not going to ground, it's going to this pin of the chip. And in this way, we are able to achieve much higher voltage swing using limited voltage supply. In my test project, I have used the exact same schematic given in the datasheet. However, I have just replaced this feedback resistor with a 50 kilo ohm potentiometer to be able to control the gain. However, for a device like this, increasing the gain will also increase the distortion, as we will see very soon in our test. At this point, I went to KiCad and laid out a very simple circuit for this audio amplifier chip, which you can see here. There is not much about it. Then I have exported the fabrication files and went to JLCPCB to place my order. And this is our sponsor time. JLCPCB is one of the largest PCB manufacturers in China. They offer amazing quality services for affordable and competitive prices. You can get up to 4 layers PCB, 5 pieces for only $2. This is 10 by 10 centimeters, and up to 8 layers for 5 by 5 centimeters PCB for only $2 as well. They also offer flexible PCBs very affordable PCB assembly service with a huge stock of parts that you can get for very affordable prices as well. They also have a high quality 3D printing service and CNC machining service and a huge stock of mechanical parts that you can use for your projects. Register for a new account using the link in my description and you will get a $60 discount coupon that you can use for your projects. And now let's upload our project Gerber file, place the PCB assembly order and move on with our project. After uploading our Gerber file, we will also have to upload our BOM file and component positions file for a PCB assembly and pay for the order and wait for the delivery. And here is the final result after receiving my boards. I will solder some pin headers and the potentiometer. And now let's move to the test bench and start testing our audio amplifier. And here is our audio amplifier PCB. I have soldered this potentiometer and I'm using a larger bypass capacitor because the 1 microfarad capacitor mentioned in the schematic is not enough for bypassing the power supply, so I'm using this 100 micro. And I'm using this 4 ohm 5 watts dummy load, resistive load, instead of using a speaker because it's going to be very loud during the power test, and this audio input jack to use the line output from the computer, which we will also test in a moment. Before beginning our test, let's leave this aside for a moment and take a look at this. This is my MIDI keyboard. It has a TRS MIDI output jack, some interfacing electronics, and this is the old project that I told you about that I was reworking. This is a capacitive touch sensing piano project that has been sitting there collecting dust for almost 6 years, despite the fact that it was very successful back in the days. Let me play a very short demo for this project. What you have just seen this PCB project doing is the microcontroller here, which is a microchip PIC microcontroller, is sampling all of these capacitive touch sensing channels, doing some digital filtering and stuff, and sending all of this data over UART to the PC, which has the audio synthesis ADSR software that plays the actual sound. So this was just the front end and it was successful. The objectives of the rework and upgrade for this project was to make everything happening all on the same device. I wanted this device to do everything from the capacitive touch sensing to the audio synthesis and the MIDI input and MIDI output to be able to communicate with this MIDI keyboard, and it should also have an audio power amplifier on chip capable of driving actual speakers, so it will become a standalone USB power device. I will also take the chance of being here on the bench to show you a couple of other projects. If you want to see more of this content, please consider subscribing to this channel and turn on the notification bell to stay connected, and consider leaving a like or a comment on this video if you do like it. It does help for the algorithm that for some reason hates my channel, or maybe because I'm not that active, but there are many projects in the coming in the way, and there are many projects that I have here just like this. This is a step down buck converter chip that costs only $1 and it's rated for 24 amperes. And here we have it on a 6-layer PCB. Maybe this will be in the next video. Here we have also another project on the bench. This is a Raspberry Pi Pico 2 with ESP32C3. And there is an SPI bus connecting between the chips, and it should be an interesting board to have a look at. And this may also be in the next video. I didn't decide yet, so stay tuned and let's get back to our project. Now I will hook up the 5 volts to the supply of this audio amplifier, and I will use my function generator to generate a 1 kilohertz tone, and I will measure the output on this or across this load resistor using the scope. Here is the power. And let's hook up our function generator to the input. Now we have the power connected, we have the signal generator connected, and we need to connect the scope. And now we have everything connected. I will enable the signal generator output, and I will keep increasing the amplitude of the input signal until the output gets barely into the clipping. We don't want to take the measurement when the amplifier is deeply clipping, so I will increase the input signal. Yes, at this point, just barely before clipping. Yes, at this point I will stop here. Stop the signal, and this is where we take the power measurement. The audio power output is given by this equation, which equals VRMS squared by R load, and as you can see, the measured RMS voltage is 1.6 volts. The load we are using here is 4 ohm load, so the output power is about 0.64 watts. So we can expect an 0.6 watts of clean audio power. We can actually get more power but the audio signal is going to be more distorted than this. We can also use the V peak to peak value here in this equation. However, if this signal is not sinusoidal anymore and it gets distorted, you have to use the VRMS value. The root mean square value is the more accurate value to use for the power calculation, especially when the signal is not sinusoidal anymore. Just like what we are going to do now, I will re-enable the signal and I will increase the amplitude, so we have more VRMS. I guess this is more than 10% THD. Yes, let's stop at this point. Let's take our measurement and we have like 1.8 volts VRMS. This gives us 0.8 watts of power, which is not a clean audio, as you can see. And of course, this is not what was promised in the datasheet. Anyway, we have now completed the power measurement of this audio amplifier. Now we will move to the THD or total harmonic distortion measurement. For THD measurement, you typically need to have a very high dynamic range for your measurement of the output signal. A typical scope is not designed for this. It has a vertical dynamic range like maybe 8 bits in resolution, 10 bits, 12 bits. It's not very practical to use scopes for measurements like this that needs a very high dynamic range in the vertical axis. This is what I'm talking about. Scopes are very fast in the x-axis, not in the y-axis. Here we have a 1 gigasample in the time axis. However, in the voltage axis, it's very limited in voltage resolution compared to something like this SoundCard, which has 32 bits audio DAC and 32 bits audio EDC, which provides order of magnitude better measurements for THD. This SoundCard, for example, can achieve negative 110 dB. Out of the box, this SoundCard can achieve up to 0.003% of THD. With a notch filter on the back end for the generator and distortion magnifier for the front end, we can reach up to maybe like negative 150 dB, which can give us some phenomenal numbers in terms of THD. I will use both tools to take the THD measurement, but in this video I will show you how to do it using a scope, and I will leave the SoundCard THD measurement setup for another video. So let's enable this signal and I will decrease the amplitude just barely before getting into clipping. Yes, let's take the measurement at this point. Then I will take a lot of samples before I enable the FFT mode. Center at 5 kHz, 1 kHz per division. And this is the FFT analysis for audio output signal from the amplifier. And here is the first order or the fundamental harmonic at 1 kHz generated by the function generator. And those are the harmonics that we need to measure to identify the THD. So I will enable the cursors and I will put one cursor at the tip of the first order harmonic and I will move the other cursor at the second order harmonic. And in this way, the delta Y measurement is the DBC value, which is the difference between the second order harmonic and the first order harmonic. I will keep doing this, the same step, to take the DBC value for all of the other harmonics. And now let's save this measurement for the second order harmonic. It's negative 32.8 dB for the second order harmonic. And I will move the cursor for the third order harmonic, which sits at negative 51.6. And I will keep doing the same for the other harmonics. And here are our measurements. Let's now jump to the PC to show you my calculator that I will use to find out the THD value from these measurements. And here we are. This is the THD calculator. I will leave a link to it down in the description, and let's inject the values that we have taken from the scope. I will leave the first order harmonic or the fundamental at 0 dB because we are measuring the DBC and I didn't have to adjust the reference level for the first order harmonic, so we will leave it as it is. And we will start with the second order harmonic, which was negative 32.8. Third order was negative 51.6, and so on. I will keep filling these values, and as you can see, the THD measurement is 2.3%, which is negative 32.5 dB, which is not too bad actually. And this is the THD measurement using my SoundCard setup. By optimizing the input level and so on, I managed to achieve negative 48 dB THD, and the noise floor was setting at negative 71 dB. This is my 1 kHz tone generated by the SoundCard, and those are the harmonics, and this is the peak performance we can expect from this amplifier chip. As you might have noticed, these THD numbers are very good, but the catch is that we have to take down the power down to 0.6 watts to reach these very good THD numbers. And this is not what was promised in the datasheet actually. If we get back to the datasheet, even when the sine wave was completely distorted, I was not able to get anywhere near these numbers shown here. And this also applies to all of these characteristics curves. So I guess this is the limit of this audio amplifier chip. At the end of the day, 0.6 watts of clean audio power output for only 2 cents is not very bad, to be honest. I will do one more sound test before concluding this video, so let's get back to the test bench. We will use this capacitive touch piano along with the computer software to do the audio synthesis, and we will take the line output audio signal coming from the PC to this audio amplifier, and we will replace this dummy load with actual speaker. I will use this speaker, which is 4 ohm 5 watts, and we will play some music using this setup. And here is a diagram showing what is going to happen. Our CapTouch PCB project will capture all of the keys and send the data over UART to the PC. And on the PC side, there's a software that does the ADSR audio synthesis. And we will take the line out coming from the PC over this cable, and we will hook it up to our audio amplifier just like this. And we will replace the dummy load with an actual speaker to listen to the actual sound coming out of this audio amplifier. So let me complete these connections. I'll stop testing at this point and let's jump to the conclusion. The sound quality coming out of this audio amplifier is really good. It's not bad actually. However, the audio power or the clean audio output is very limited, especially compared to what was advertised in the datasheet itself. And that's why I didn't choose this audio amplifier chip for my project rework. And here is what I have selected for my project. It's the LM4871 from TI. This is another low voltage audio amplifier chip that can be supplied using only 2 volts up to 5 volts. So it's very convenient for USB powered devices, exactly what I need for this project rework. 10% THD for 3 watts of power into a 4 ohm load isn't what I'm looking at. Let's check the clean output audio power. At 1% THD, we can expect 2 watts of power into a 4 ohm load, and I believe that the actual performance of this audio amplifier chip will be very close to what is advertised here in the datasheet, and it's not very much more expensive. It's like 50 cents, and I have used it here in this upcoming project, so stay tuned if you are interested in STM32 audio synthesis. And here is the audio amplifier chip, and we can test this audio amplifier chip as a standalone amplifier, or we can test it to generate sound from the STM32 microcontroller, which we will see very soon in the future. And this is the end of this video. I hope you have found it helpful or inspiring in any way. If you want to see more content like this, please consider subscribing to this channel, and I will catch you in the next one.